Ja, guten Abend zu unserer letzten, etwas späteren Session heute Abend. Wir haben jetzt noch einen ganz besonderen Gast aus Kalifornien, den VP Marketing von Scaleflux. Welcome, GB Baker. You're the
Thank
VP
you.
Marketing of Scaleflux, and we will talk about computational storage. JB will tell us what it is, what it's good for, and what they do different. JB, your stage. Thank you very much.
All right. Thank you. Good afternoon. So yes, we're going to talk through alleviating data center pain points with computational storage. So the first, just quickly give you a quick intro to Scaleflux and then what is computational storage, since it's a relatively new term in the industry. Then get into what pain points it can help address and a few case studies of customers that we've worked with to help them out. So first off, Scaleflux is one of the leaders in computational storage. We were founded back in 2014 in the US in San Jose, California, with offices in China as well, doing qualification and customer support over there. We were the first to production with computational storage drives, and we are now shipping our second generation of computational storage drives. And we continue to win awards year after year for innovation and innovative work with customers in deploying flash for computational storage. Now, what is computational storage? It's a new term in the industry, and it can have a lot of blur around it. Well, about 2 years ago, we got together with about 20, 30 other companies and started a working group within the Storage Networking Industry Association. So within the standards board, all these companies got together to define and work on computational storage. The definition that is now posted on the SNIA website is here on the page, where the core things of this are that computational storage is focused on offloading host processing and reducing data movement to help enable parallel computation and alleviate constraints that have come into play on compute, memory, storage, and I/O buses. So that's the core of it. You can read through the rest when you want. Now, computational storage drive, which is where Scaleflux is focused, combines a enterprise class PCIe SSD with some extra functions that are handling this compute offload. So we're putting two capabilities into a single package. Now, why bother with computational storage at all? Well, in the traditional processor-driven architecture, things were great for a while, but when you had hard drives and then maybe SATA SSDs feeding tens or maybe a few hundred megabytes per second, but now with NVMe SSDs delivering over 3 gigabytes per second per drive now, and then transitioning to the order of 6 gigabytes per second per drive with PCIe Gen 4, we're creating bottlenecks at the CPU and the host memory. And even when we try to offload processing to FPGAs or accelerator cards, we can still suffer from bottlenecks on those buses. So that with the traditional architecture, we don't have a lot of parallelism. We've got all those bottlenecks. There's limited slots for those FPGAs. You've got to move a lot of data around, and it creates a lot of challenges for scaling. Now, when we shift to a data-driven architecture, which is enabled by computational storage, what we're doing is moving some of those compute functions down into the drive to work on the data where it lives, which helps minimize the data movement, enable much greater parallelism, because every drive bay now is also a compute bay, which that helps with the scaling. We've now got multiple FPGAs and a much more balanced architecture between compute and storage I/O. Now, the types of functions that could be pushed down into the drive or into a computational storage processor are things that either are going to be done on a large portion of the data set or maybe aren't handled very well in a general purpose processor that can be handled better in a hardware engine, such as compression, encryption, and then even data filtering and inferencing and video transcoding, which are things that Scaleflux and others have brought out to market today. We're going to, in the case studies, I'm going to focus on the compression and the data filtering, which are the features that we offer. And then other things that are coming in the future are going to be additional query acceleration for databases, and then things that work with both the software and the hardware being developed together to synergize, such as database optimization and data preparation, and then additional accelerations for machine learning and artificial intelligence, things like intrusion detection, identifying different types of data that are suddenly flowing to your drives, fuzzy search, and others that will come out to solve additional problems. Now, the key pain points that computational storage are focused on are really application performance, where we're going to increase the performance of those enterprise applications, queries per second, transactions per second for databases, reducing the latency, and then also alleviating the bottlenecks, as I talked about at the processor and storage buses and the network level. Then the second side of this is dealing with cost, helping reduce cost as companies are having to scale their infrastructure dramatically to deal with the rapid growth of data. So helping to reduce the acquisition cost of new equipment to service that, the operating costs, and then translating that into better efficiency, cost per query, cost per transaction, or cost per gigabyte of user data stored. And all these can apply to any enterprise application. We have been focusing our testing on enterprise databases, which are kind of the fundamental behind a lot of applications that people are providing out to their customers. So now first on that queries per second or application performance side. Here what we're looking at is testing of MySQL by Percona. They did this test in conjunction with our drives. And what we see here is that with ordinary NVMe drives, represented here with the dark gray, they achieve a decent level of performance. But then if you try to use host compression, it burdens the CPU and it slows things down, as shown with the light gray bars. When we put in a computational storage drive, which has integrated transparent compression and decompression, it utilizes that compression, decompression to reduce the amount of writes that are happening to the drives, which boosts performance and gets us to higher queries per second, as shown in the light blue. And then additionally, our drive can support atomic writes, which allows you to turn off the double write buffer that is ordinarily required in MySQL to avoid data loss on an unplanned power failure. And that can give an additional boost to the performance. On the latency side, we're going to look here at Aerospike. Aerospike is an extremely latency sensitive database used for advertising technology, financial technology, and fraud detection, among other things. Their key metric is the percent of read transactions that take more than 1 millisecond. And to pass their test, you run the test for 24 hours, and to pass the test, fewer than 5% of read IOs can happen over with that 1 millisecond buffer or barrier. Now here with ordinary NVMe drives, what we see is that they were able to complete the test at a pressure level of 360,000 transactions per second, but failed the test with 5.5–6% of transactions taking more than that 1 millisecond. When we put in a computational storage drive with that transparent compression, decompression, we're able to take advantage of the patterns in the data to improve performance and reduce the percentage of outliers. So here, the ScaleFlex drive hummed right along at less than 1% outliers for that entire 24-hour period. So overall, 98% fewer outliers than the next best NVMe drive. So it's dramatic improvement for latency. This also can translate into better transactions per second for Aerospike, and even better costs for Aerospike. So here, this first set of bars is the maximum level that each drive could pass that Aerospike test. So we have a couple of NVMe drives that passed in the 250 to 300K range, and then with the computational storage drive exceeds 500,000 transactions per second. And then a different skew of the drives set to a little bit lower over provisioning, here a 3.84 terabyte drive. The ordinary NVMe drives drop off dramatically, under 200,000, where with the computational storage it can still exceed 400,000 transactions. And then on the cost side, what we do is we say, hey, we're doing that compression in the drive. Can I use that compression to store more data? Sure. So what we do is say, use that compression, configure this 4 terabyte drive to 6.4 terabytes of user space, and then run the test. And what we see here is that that configuration is still able to pass at almost 400,000 transactions per second. So over 1.5 times the performance of the next best drive, while delivering twice the capacity to reduce your overall infrastructure cost. Now shifting to the alleviating bottlenecks. The first thing is around the I/O buses. And this is going to translate to alleviating bottlenecks in other places. So in this example, what I'm saying is, hey, look, I've got a database that's 12 terabytes. It's spread across 4 drives, and I want to run some analytics on this, and I want to do some investigation around the records that were just from a 3-month period in 2016. And so those records really only comprise, say, 100 gigabytes or 0.1 terabytes of this entire 12 terabyte data set. But to run the analysis, ordinarily what I've got to do is pull all of that data up, run my filtering to find the right data in the CPU, and that takes time and causes a bottleneck up at the CPU and on the I/O buses. Now, with data filtering down in the drives, I can identify that the data, before it has to leave the drive and pass across the PCIe bus up to the CPU. And so here we only have to move that 100 gigabytes of data. Now, in a little more techie benchmarking here, we investigated that capability, and we were running analytical queries on multiple instances of RocksDB in a server. And what we see is that with ordinary storage, what happens is when we go from 1 to 2 to 3 to 4, the blue to orange to green to red number of instances, the CPU becomes, which is the left or the y-axis, becomes bottlenecked. It becomes pegged right about those 4 instances. And when we go to 5, 6, 7, 8, we just have to wait. It creates much greater latency on completing the queries. When we do the filtering down in the drives, what we see is that we never run into bottlenecking the CPU all the way up to 8 instances. And we're reducing the query times, which is the right end of each of those bars is how quickly the query finished. And then if you think of the CPU resource that was consumed, it's really represented by the area under the curve. So without filtering at the drive, you can see how much more space is consumed, how much more CPU resource is consumed when you're doing the filtering at the CPU instead of filtering that data out at the drive. Now, switching over to cost, what we see is, and this is going to relate primarily to the compression decompression. What we see is that data, particularly database data, is highly compressible. So actually, our chief scientist before or just after joining ScaleFlux and his students did research out in the industry on different types of data and how compressible they were. They found that database files tended to be greater than 2 to 1 compressible. And then over the last 9 months, while we've been sampling the CSD 2000 and out to customers, and they've been testing their data, we're getting feedback that verifies those results, that in real world use cases that customers are seeing anywhere from 2.5 to 5 to 1 compressibility on their data, which means that, say for a MySQL instance at 2.5 to 1, or at 5 to 1 compression, they could reduce their storage footprint by 80%, okay? And so that is going to translate into significant cost savings. So here to try to give you a little example of it, let's say we had a 10 petabyte deployment. Without compression, you're going to have to buy that full 10 petabytes of storage. If the data is 2 to 1 compressible or 3 to 1 compressible, you can reduce the amount of physical storage that has to be purchased down to 5 petabytes or 3.3 petabytes. And that is going to translate into significant cost savings, even with a premium on the CSD drives. So, here at 20 cents a gig, cost you about $2 million for that 10 petabyte deployment. With ordinary storage, using computational storage at 2 to 1 or 3 to 1, you can cut that cost down up to half. And you could actually extend beyond the 3 to 1. I'm just showing the 3 to 1 here. Another piece of that is that when we're reducing that physical footprint of the storage, there may be the additional capability of reducing the number of servers that you have to use to achieve the performance and storage capacity. So now on cost, on the other side of TCO, the operational cost. So the first thing we look at here is what is the total power to service all of this? And when I have no compression, I've got a certain level of power. If I use a host compression here, two different options, LZ4, which is a lightweight compressor, or zlib level 6, which is a very high level compressor, but consumes a lot of CPU resource. Utilizing either of those is going to add on to the power that's consumed by the CPUs, which is going to offset any savings that you get by reducing the power for the drives. When you use computational storage, you're not adding on that CPU power, so you get to just reduce your overall power by cutting the number of drives that have to be utilized. Then another thing is the software licensing here. So without any compression, I got a certain level of software licenses. When I switch to, say, LZ4, I'm adding some burden on the CPUs with by doing the compression, but I might be able to get rid of some of them because I'm cutting down the number of drives and potentially the number of servers. So maybe about the same on software licenses, but probably a little bit higher. With zlib level 6, it's extremely burdensome on the CPU, and what we see is that to achieve the same level of throughput, it's going to take up to 5 times the amount on the CPU. So now we're significantly increasing the software licensing. With the CSD 2000 or with a computational storage drive doing that compression, we're reducing the number of servers, we're reducing the number of drives to achieve the same level of performance and throughput and saving on software licenses. And then in terms of physical footprint, the same thing can happen here where, okay, I've got my baseline footprint, and when I do compression with LZ4, maybe I can save a couple of servers by reducing the number of drives, but I'm not getting that same level of compression. If I go to zlib level 6, well, I'm saving on how many drives I need, but I'm adding on to the CPUs, which is probably going to increase the number of physical servers I need to have and put into my infrastructure. When you use computational storage, you could potentially reduce the number of servers that you physically have to install to achieve that performance. And then in terms of the efficiency level of cost per unit of work, well, we've talked about reducing the acquisition costs and reducing the operating costs, and at the same time, improving the performance of the applications. So, you put all that together, and of course, that's going to drive down the cost per query or the cost per job or the cost per transaction. So your efficiency metrics can improve utilizing computational storage. Now, in practice, we've got a few case studies here. This first one is Alibaba, where their goal was to reduce the cost of scaling in order that they were incurring to serve a rapidly growing hybrid transactional analytical database that they have deployed called PolarDB. The key problems here was that they're running analytics and transactions, but when they put the two of them together on the same data set, it really slows down transactions. That forced them to have 2 copies of the entire data set. So they would have to take a snapshot of the transactional data to make it available for analytics. Then that was also causing a significant burden on the network. By using a computational storage drive with data filtering, what we see is we're able to alleviate that CPU bottleneck, running the transactional processes and the analytical processes on the same copy of the data set at the same time without impairing the transactional process. So that improved performance, got rid of that second copy, so cut their infrastructure in half, and reduced 70% of the network traffic. So pretty good benefits for those guys. The second one here is a MySQL user that has petabytes of deployment, and their deployment is growing very rapidly. They'd really love to use compression to reduce the cost of their infrastructure, but everything they've tried impairs their latency too much, and they can't meet their service level agreements. So the cost of flash and then the penalty that they incurred by using compression were the pain points that they had. Using a computational storage drive with transparent compression, they were able to realize a 30% potentially higher reduction in their overall storage cost by utilizing that compression to store 2 to 4 times the amount of logical data per physical drive. And they saw that, hey, my performance didn't drop at all. I'm able to maintain the same latency levels and meet all of my performance requirements. And the last one here is an ad tech company that utilizes Aerospike. They're looking at moving from cloud to on-prem to reduce their overall costs. The key pain points they have is that in the cloud, they are using compression to store the data, but they're paying for 48 cores per NVMe SSD. They've got petabytes of storage out there, and they're saying that they're paying for over 10,000 cores just to perform the compression function, not even to run the database, just to run the compression function to service their data. So utilizing a computational storage drive, again, with the transparent compression, what we see is that we can cut that CPU burden from 48 cores to less than 1 per 2 gigabytes per second of throughput, or per drive. And that is going to allow them to efficiently scale their throughput and efficiently scale their overall infrastructure. So in summary, computational storage is there to help alleviate bottlenecks. It moves tasks such as compression, encryption, data filtering from the CPU down into the drives, which enables parallel processing and reduces overall data movement. It improves the application performance. You can get immediate benefits for both the compute and storage by utilizing computational storage with your enterprise databases. It improves TCO by reducing the acquisition cost, storing more data per physical gigabyte of flash, and reducing the amount of flash and potentially the amount of servers you have to buy, and reducing operating costs. Again, lower power, potentially significant savings on software licenses as well. And computational storage is just getting started. Products have just launched over the last 2 years. There's a lot more to come as in this new area of the industry. And for more information, you can visit our website, scaleflux.com. We've got product information and videos about the technology as well. Or you can email us at info@scaleflux.com to see about doing any sampling. So with that, I appreciate your time. Open for questions.
Thank you very much, JB. Interesting presentation. I have just one question before we come to Wolfgang's. You said it's just the beginning. So do you have kind of a roadmap where it's gonna go in the next month, years? What do you expect?
Yeah, we actually, I mean, of course, we have our next generation product already in development, right? We've got to start developing as soon as or before we launched the second gen. So we'll be adding on additional features that were in that list of computational storage functions that I had very early in the presentation. So we'll be pulling more of those features into the next generations of products.
Sounds good. Sounds good. So sounds like we have to do another vendor talk with you soon. So Wolfgang also has a question. I have to get a little bit closer. I'm old and my eyes are not so good anymore. As far as I know, ScaleFlux uses FPGA while competitors use ARM for computation on the device. What are the reasons why ScaleFlux uses FPGA instead of ARM
Sure.
processors?
So in in the first couple of generations of product here, we were using FPGA, which allowed us much greater flexibility in adjusting the workloads and in adjusting the functions that we were providing to meet customer needs. So with a brand new category of product, we needed that flexibility so that once we started going out and talking to customers and we identified that, oh, well, maybe, that compression was the key thing they were focused on instead of erasure coding, for example, then we can reprogram the FPGA, take the same hardware, and solve their problem, right? So that was one of the core things there. Another one is that with the FPGA, we're able to put things into hardware engines. So the compression, decompression, the data filtering, those are done in hardware engines, which are able to execute the tasks much more rapidly than we can in software running on a general purpose core, like an ARM core. So it's just a little bit different focus for the companies as well. We're very focused on functions that are going to be very broadly applicable. And then I know that for some other computational storage vendors, they're more focused at edge or different aspects that require additional core capability.
Am I, as a customer, be able to program FPGAs by myself, or is it hardened by you?
There's no need to program the FPGA for
Okay,
customers. So
but I
that's
can.
actually, yeah. We're programming the FPGA, and we validate the entire product together with the firmware, the software, the hardware, the flash. So all of that is hardened and tested together. So there's no knowledge, no FPGA knowledge needed by customers. There's no application integration required. And we focused that for the generation of products here because we wanted to make it a turnkey solution to make it as easy as possible for customers to use. In future generations, we will be looking at a more platform approach, which in addition to having a turnkey, we would open up capability for customers to add their own IP into the FPGAs.
Okay. If I'm large enough, will you program FPGAs dedicated to my needs? If I pay you?
We are open to discussions with major customers about optimizing the product for their specific applications.
Okay, good. So Wolfgang has another question. Will the hardware be able to run more than one different workload or code at the same time? Is this feasible anyway?
Yes, well, you can run any application you want, and it's going to transparently take advantage of the computational storage function that we've integrated. In this generation of product, the data filtering and the transparent compression are two separate firmware loads that do not run at the same time. So it's either data filtering, which is more specific to MyROX, RoxDB, and then there's the transparent compression, decompression, which is applicable to every application. In future generations, where we will be able to integrate more functions into this at the same time. Right now, we do have a limit on, we use a relatively small FPGA to stay within the power envelope of an ordinary U.2 drive and a low profile add-in card. So we use a relatively small FPGA that limits the number of functions we can put at the same time.
Can the customer change the firmware he bought once when he has to change workloads or approaches?
Yes, we can do firmware upgrades in the field. So it would be getting getting the firmware from us and then download it to the drive, update the drive. Now, if you're going to switch from data filtering to transparent compression, decompression, that would probably require a reformat of the drive. You're going to want to move your data off before you do that. But ordinarily, if you're just upgrading from one gen of firmware to the next gen of firmware within the transparent compression, that can be done live. It's a very brief interruption to I/O to the drive. and there's no
Okay.
data loss, no reformatting required there.
Okay. And now need to buy another hardware or
Right.
just, yeah, excellent. Good. Thank you very much